Dimensional analysis and its applications. So now we are learning the applications of dimensional analysis, and in this part we'll take the dimensional consistency of equations. So this is the first application of dimensional analysis. It is checking dimensional consistency of equations. Now I'll tell you what dimensional consistency and actual consistency actually means. So I'll tell you, and let's actually write an equation. Let's write the equation. We know the kinematic equation of uniform accelerated motion. S is equal to ut plus half a t square. So basic equation, and we know the equation is right, but we have to prove it is right? So in order to prove it is right, let's write this all the terms in the term of dimensions. So what is S? S is displacement. What is displacement? Displacement is just another form of length. So we write S as L, okay, equal to U. U means initial velocity. So initial velocity is L into t minus 1 times time t plus half A is. Now for writing equations we generally don't write the numbers because the numbers are dimensionless constants. We don't write numbers or constants in a dimensional equation, so we can avoid the half, right? When we are writing the dimensional form of this, don't write the half because that's dimensionless. Or like all the fundamental quantities are raised to 0. Just imagine a number is when all the fundamental quantities are raised to 0, so it's just 1. So we don't write that. Acceleration is L t raised to minus 2 meter per second square, and time square. And if we solve this, L t minus 1 into t, so we can solve using algebra of exponents. T minus 1 plus 1, so minus 1 plus 1 raised to equal to 0. So L t raised to 0 plus L t minus 2 into t square, so t 0 itself. So t 0 is 1, so L only, so L plus L. Now saying this, you might think you can write 2L. Well, even if you write 2L, 2 is a dimensionless constant, so we can just avoid it and we get L equal to L. So there is no use of that. So what does this say? We just got L equal to L plus L. So what does this say? This actually states that this equation is correct by the principle of homogeneity of dimensions. I'll read the principle and explain it to you. The magnitudes of physical quantities may be added together or subtracted from another only if they have the same dimensions. This simple principle is called principle of homogeneity of dimensions. If the dimensions of all the terms are not the same in any one side of the equation, or LHS and RHS of the equations contain different dimensions, the equation is wrong. So we see in any one of these sides, if the dimension was like, if we had another term L t raised to minus 1, if we had another term, then these dimensions won't match with this, then we can say the equation is wrong. But since we don't have this term and these terms are alike, and these terms are alike to the LHS and RHS are both alike, right? So we can say this equation is correct by the principle of homogeneity of dimensions. So what did we say? It says that we can only add and subtract dimensions if they are of the same dimension. So these are of the same dimensions, so we can write L plus L is L itself. We don't write the 2L because 2 is a dimensionless constant, so we just got LHS equal to RHS, right? Hence this equation is dimensionally correct, okay? But we didn't actually prove, like, if for example we write another equation, S is equal to 5 ut plus 3 at square. Even if we do this, we can write L, right, equal to 5. 5 is a dimensionless constant. if we solve this, ut is L itself. By here, I'm not going to do the same thing. 3 is a dimensionless constant, at square solved up to L. Here also we got LHS equal to RHS. But does that mean that this equation is correct? No, we just made that equation right up this instant. So even though this equation is dimensionally correct, it is still an inconsistent equation. So what does this say? It says that if an equation fails the consistency test, it is always wrong. So if this was not the case, like for example, x is equal to ut square, we just wrote that, and we write L. If we write in dimensions, we get LT, L equal to LT. So LHS not equal to RHS. Then we can say the equation is totally wrong. It's not dimensionally wrong, it's totally wrong, because it's not, even if it's dimensionally wrong, it even if it's dimensionally right, it cannot be a correct equation, as we saw here. But here it is dimensionally itself wrong, so that means that equation is totally invalid. So that's what I said. If the equation fails the consistency test, it is proved wrong. But if it passes, it is not proved right. Thus, a dimensionally correct equation need not be actually an correct equation, but a dimensionally wrong equation or inconsistent equation must be wrong. So that means even if this passes the consistency test, we don't really know if it were the valid equation. So we can somehow validate this is dimensionally correct, but it's not the actual equation. This was the actual equation, this is the wrong equation, but this is also dimensionally correct. This is dimensionally wrong and inconsistent also, so we can definitely say that is wrong. But for this case, we are unsure, and hence scientists often use dimensions to first check if the equation is dimensionally correct, then they go for proving that equation and finding the actual coefficients of these terms. Okay.